Welcome to another video for MS100. In this video I'll be focusing on work, which is a grade 12 topic, and the outcome for this lesson is to understand the forces which are acting at an angle, right? So it's actually to understand the work done by forces which are acting at an angle. So with an aid of a diagram, so say again we have an object of mass 5 kg, okay, and then we have an applied force which is applied at an angle of 30 degrees, and this object is initially resting on a horizontal surface at point A. Okay, so now the applied force, which is 100 newtons, it causes the object to move from point A to point B, which is 5 meters. Alright, so it means that as this force is applied, it moves the object from point A to point B. Okay, so now we want to understand how many forces are acting on the object, and we do that by drawing a free body diagram, right? So now, an extra information: the surface is smooth, it's not rough. The surface is smooth, meaning that we do not have friction. Alright, so the direction of motion is from A to B, which is to the right. Okay, so we can draw our free body diagram now. Our free body diagram would have the mass, because we have, it will have gravitational force because we have mass of mass 5 kg, and then we have our normal force since we have our surface, and we have our applied force which is applied at an angle, and there is no friction because the surface is smooth. Okay, so now this force, or this applied force, is applied at an angle of 30 degrees. So now we want to understand how can we actually calculate the work done by this force which is at an angle of 30 degrees, right? So now, for simplicity, for you to understand whether a force does work or not, okay, we can specify the direction of the displacement in the free body diagram, and we can see that the normal force is perpendicular to the direction of the displacement, so this one does not do work. And FG in this case is perpendicular also to the direction of the displacement, so it does not do work also. But now, how can we actually calculate the work which is done by a force which is at an angle? So now there can be two ways actually. So the first approach is that you have to find the angle between the displacement and your force, and in this case you can see that the displacement is to the right, so it's horizontal to the right, and you can see that in this case your force, or your applied force, is 30 degrees from the horizontal, so it means the angle between your displacement and your applied force is 30 degrees. So now you can simply compute, or you can simply calculate your work done by that applied force, which will be the force multiplied by your displacement multiplied by your cos theta. Okay, and then your work done by the applied force, that would be equal to your applied force, which is 100 newtons in this case, so that would be 100 newtons, and your displacement is 5 meters, and then multiplied by the cos of the angle between the two, so the angle between the two is 30 degrees, so that would be cos 30. So now it means that your applied force would be equal to 100 multiplied by 5 multiplied by cos 30, and that would give you 433.01 joules. Okay, so now the second approach is that we can actually resolve this force into two forces. Okay, so if we resolve this applied force into two components, then we would have your vertical component, which is your F applied in the y direction, and would have your horizontal component, which is F applied in the x direction, right? And now we can see that the F applied in the y direction, that would be your F applied sine theta, and then that would be your F applied cos theta, right? So this is actually covered in the topic whereby we resolve forces. So we can see that in this case we have two components of the applied force. One component does work and the other component does not do work. So if you check this y component, the direction of the y component is actually perpendicular also to the displacement of motion, okay, or to the direction of the displacement. So it means this does not do work and it's in the same direction as the normal force. But now if you check your horizontal component, that component does work. So you can actually calculate the component, which is your applied force cos theta, which is in the x direction, right? So your applied force in this case, it's 100 cos 30 degrees, and that would give you 86.60. All right, so now we can see that the force that does work is the horizontal component because it's in the direction of the displacement. Okay, so now if we were to calculate the work done by this horizontal component, then we would say work done by that horizontal component, which is equal to the horizontal component multiplied by the displacement and then cos the angle between the horizontal component and the direction of the displacement. So in this case that would be 86.60 multiplied by 5 and then multiplied by cos. So now if you look at the angle that we're going to use now, this is the force, right? And this force is in the same direction as the displacement. So now the angle that we'll use is 0 degrees. So it means that would be cos 0, and that would give us 433.01. So we can see that this answer is actually the same as this answer. So there are two approaches that we can use. If we have a force at an angle, we can use the angle as it is, but now we must make sure that the angle is between the force and the direction of the displacement, or else we can start by resolving those forces which are on an angle, right, or which are at an angle, and then we take the components of those forces which do work and calculate the work, and the components which are perpendicular to the direction of motion, those components do not do work.